cataclysmos, which means destruction of the world by water, and this means destruction of the world by fire. And those were the two principal ways that the ancient peoples saw that the world was periodically destroyed. And when we first started this whole series, I presented quite a bit of evidence to try to convince you that there really was a historical basis to the idea of these tremendous great floods. And if you were paying attention, you knew that I was trying to insinuate that the scientific explanation went back to the end of the last ice age, with what I refer to as the Great Meltdown. So what was the time period? Jerry, when did that happen?
Between 12 and 13,000 years.
Very good. You were paying attention.
And you also called it the Great Melt-Off.
The Great what?
Melt-Off.
Melt-off? Meltdown, melt-off, yeah. And one of the things I presented in here was information that there was a source of energy that at this point still has not been identified. It was first... the realization came upon researchers in the early 70s that the glacial ice, this huge, huge amount of glacial ice, had melted so fast that they couldn't account for the energy source necessary to melt the ice that fast. And they struggled with it. There was a series of articles that basically were in the scientific literature from 1973 to 1976. And then I pretty much, after that, you don't see much about it anymore, because if you read the tone of the articles towards the end of this period, they're almost sort of giving up in desperation, saying, well, maybe there's an error in our data somewhere. You know, maybe this, they essentially just gave up on the problem, okay? Because what had happened is in the old models, they had 30 or 40,000 years to melt the glacial ice away. But then with the advent of radiocarbon dating, 2 decades of accumulating radiocarbon dates had shown conclusively that the ice melt-off was considerably less than 10,000 years and not 25 or 30 or 35,000 years as previously assumed. As the dates begin to get more and more refined, even that 10,000 year period began to contract dramatically to the point where it appeared as if the whole complex of ice was still there 13,000 years ago, and by about 9,000 years ago was pretty much gone. Okay, so what happened even between the early 70s, when this, what they referred to as the energy paradox, first became apparent, and now is that the problem has become even more acute. Because in the 1970s, they were struggling with an 8 or 10,000 year melt-off period. Now, with the data we have in hand now, suggests that the melt-off period did not exceed 3,000 or 4,000 years. And the second thing is, if you remember, I've shown you this graph now several times of the rates at which meltwater entered the ocean, and you could see that it was not uniform between that 3,000 and 4,000 year period. There was actually 2 extreme spikes of meltwater that flowed into the ocean, and which in a sense makes the whole problem that was originally posed back in the early 70s even more intractable. Because if they were not able to provide a source of energy to melt the ice within 10,000 years, how do you essentially explain the melting of the ice over 2 very short intervals, which may have lasted no more than a few centuries each, maybe even less than that? Now then, coupled with that is the evidence right from the field itself that there have been catastrophic flooding all over the world. And I've shown you slides of some of the features out west and some of the features right here in our own backyard. The things around here are more subtle and difficult to identify unless you've been shown or trained to read the landscape, and you can understand when you look at a clay deposit, for example, and you see that there's a gravel lens in it or a gravel layer sandwiched between 2 layers of clay, you know that that clay has been subject to flowage. The clay deposits around here are essentially deteriorated bedrock, is essentially what they are. And in some places you can dig down through the clay, and actually you'll see where the clay grades into the granite bedrock. Lots of feldspars in the granites of Georgia, and feldspar weathers into clay. But in other places you can see very clearly where the clay has been subject to extreme flow events. No dating has been done on these flow events. I would predict if dating was done, though, it would date back to this same interval, that transitionary interval from the ice age from the glacial age into the interglacial age that we're in now. If we go north of here, up into the mountainous areas, then we can begin to see the evidence quite spectacularly, where primarily in the form of boulder streams, cataracts. A lot of the North Georgia, Tennessee, and North Carolina waterfalls are flowing over cataracts. They're difficult to identify, more difficult to identify than say the dry cataracts out west that I've shown you slides of, only because of the climate of the southeast causes so much more rainfall, and the rainfall in turn causes lots of vegetation to grow, and so it obscures them. And you might be hiking up in the North Georgia woods and walk by a waterfall and not realize that it's a remnant flow over a much larger cataract feature that once sustained a much, much greater flow than is now present in the modern creek. Whereas when you're out west, these cataract formations are very obvious because, you know, especially in the desert regions. And when you go, I don't know how many of you have spent time in the deserts, but if you go in the desert and you actually begin to examine the structure of the desert, you begin to see that virtually everything you see in the desert was created by water. Even though it's completely arid and you go into the Sonoran or the Mojave Desert here in the U.S., you might have 2 or 3 or 4 inches of rainfall a year at the maximum. And yet everything around you is shaped and sculpted by enormous water flows. Even the desert floor itself, if you go down into the arroyos, I don't know if anybody know what an arroyo is? An arroyo is a channel, a water-cut channel that goes through the desert floor. Arroyos were almost certainly created in the last 8 or 10,000 years, the geological epoch known as the Holocene. Pleistocene was the previous one. In the Holocene is the period of relative climate stability. Okay, for the last 200,000 or 300,000 years, the last 8,000 years has been relatively stable in terms of climate fluctuations. Okay, during the Holocene, we still have flash floods in the desert, and those flash floods in the desert will cut channels that are called arroyos. You can go into the arroyos and you can actually see a cross-section of the desert floor, and it's all alluvium. You know what alluvium is? You remember the term I taught you? What is it, Sam?
Alluvium is layers of rock.
Layers
of sediment.
Layers of sediment, and how did those layers become layered?
They become by dry periods and wet periods.
Well, by water flow. And you can have sedimentary layers that can be created within one flood. You can have multiple sedimentary layers produced or laid down. And in fact, if we have time tonight, I'll show you some of the slides of the stuff that I'm talking about right now. But my point is that you can go into the driest areas of North America, and everything you see from the floor of the desert itself to the rock formations to the erosional features is all created and sculpted by water. But not water like that's there now. What is it, Ken?
Is that like the Bonneville Salt Flats?
The Bonneville Salt Flats was the bottom of a huge body of water that filled the basin and range provinces of Utah and Nevada, again, at the end of the last ice age. During the ice age, because of this huge mass of ice that covered the northern half of North America, what you had was that the jet stream was shunted to the south. So the desert areas of the southwest got a lot more rainfall than they do today. In fact, they were quite lush. There weren't deserts in the southwest 12 and 13 and 14,000 years ago and further back during the ice age. What happened is that there were lakes that formed. Lots of lakes, big lakes, okay? But somewhere around 11 to 12,000 years ago, all of these lakes underwent a massive filling. And when you say the Bonneville Salt Flats was the floor of Lake Bonneville. Lake Bonneville was one of these late Ice Age lakes that underwent an enormous and sudden expansion around 12,000 or 13,000 years ago, to the point where it rose up and literally began to flow over mountain passes. The lowest mountain passes were on the northern sector of the lake. They began to flow through, and they flowed north out of Utah into southern Idaho, where they essentially created the modern Snake River channel. And they eventually worked their way up to the Columbia River and then joined the waters of the Columbia and flowed out to the Pacific. But at its peak, Lake Bonneville was close to 1,200 feet deep. Now that's where, I'm talking about where if you go out now and you stand on the shores of Great Salt Lake. Great Salt Lake is the puddle that's left over from Bonneville. Great Salt Lake is, I'm not sure the depth of it, it's very shallow. Probably not more than 100 to 200 feet deep at its deepest. 15 feet. Yeah, it's very shallow. So, however, picture this. I mean, what you're seeing is the leftover remnant puddle of a body of water that was over 1,000 feet deep. 1,100, 1,200 feet deep at its maximum. It breached a pass on the northern rim of the lake basin. It cut that pass down by 300 feet. The upper 300 feet of rock strata was soft sedimentary rock. Below that was a hard metamorphic rock. What happened is the water began to flow through this pass. It quickly eroded down through the 300 feet of soft sedimentary rock, and when it hit that hard metamorphic rock sill, it stabilized there. Now if you go and you travel around the basin of Lake Bonneville, you can actually see the two shorelines. The one that was left at the highest water level, and then the second one that was left that was etched on the mountainsides when it stabilized at that bedrock sill. At that point, the flood that was pouring out of the lake stopped. That body of water had now dropped 300 feet, so it was now somewhere between 800 and 900 feet deep. So the lower shoreline up off the valley floor is somewhere around 800 feet, give or take. At that point, the water essentially just began to slowly evaporate away until it reached the level that it's at today. Several of the other lakes that are out there are remnant lakes. Pyramid Lake, which is near Lake Tahoe, is a remnant lake from Lake Bonneville. We can actually go to some of those slides since I'm talking about it. And the counterpart of that is that what I've been presenting in the last week and tonight is evidence and stories which I think may be pointing us in the direction of where the heat source came from. How many of you guys have been out in the Pacific Northwest? Okay, how many of you have heard of Grand Coulee?
Yep. Something about it.
How many of you have seen Grand Coulee?
I don't know.
Flew over it.
You've heard of Grand Coulee Dam,
Right.
right? Grand Coulee Dam is the largest concrete, steel reinforced concrete dam in the U.S., actually in North America. It's not the tallest, but it's the most massive.
Hoover Dam, it's a lot wider.
Hoover Dam is the tallest, but not the most massive.
Didn't we see it on one of your slides?
Probably. Grand Coulee, yes. So Grand Coulee Dam gets its name. Grand Coulee Dam gets its name from Grand Coulee. You know what a coulee is? When you're out west, what's a coulee?
French for gutter.
Gutter. Well, that would make sense. But a coulee is like a river channel with no river in it. It's like a dry channel. And they're all over the West. Coulees are all over the West, of all different sizes. Okay, Grand Coulee is the grandest of them all, hence the title.
Coulee is a little old dried up ditch in South Louisiana, yeah.
Well, it can be little. I mean, yeah, there's no, in the term, there's no implication as to size. Okay, I mean, a coulee can be a small feature. The idea is it's a water-carved channel, but there's no water flowing in it. You know, like a modern river channel has a river in it, has flowing water. A coulee does not. Well, here's the difference. A coulee is cut into bedrock usually. An arroyo is cut into the desert, the sedimentary layers of the desert floor. But really, they're probably just, you know, different terms for very similar features. Mostly you find the term arroyo in the southwest and the coulee in the northwest. I mean, so you'll see coulee mentioned, you know, you'll see the names on maps of Montana. You'll see a lot of coulees. You'll see, you know, coulees in Washington State.
That's because arroyo is a Spanish name.
All right, here's an aerial shot of Grand Coulee. Let me explain to you what you're looking at there. What we're seeing here, this whole floor of the Columbia Basalt Plateau is bare basalt bedrock that has been stripped of all topsoil. In some cases, the topsoil, which in this particular case is called loess, it's an extremely fertile material. And in some cases, it was 200 feet thick, completely stripped away. In some places here, the bedrock itself, the surface of the bedrock has been lowered by dozens of feet, and we're talking over many hundreds of square miles. Anywhere where there was a fracture or a crack or a fault line in the bedrock that provided a zone of weakness, this great flood coming across it would exploit that zone of weakness and begin carving a channel. And that's what we see here. This is actually the Coulee itself. And we're looking south here. The dam that takes its name from this Coulee is right to the north of here. And what we have here, like notice this rock, that pedestal standing in the middle of the thing. That's a remnant. Now, the estimate of the water flow that created this Coulee is between 300 and 400 million cubic feet per second. 300 and 400 million cubic feet per second. I want to give you an idea of, by comparison, the Mississippi River at its greatest measured flood stage is just peaked out at just over 1 million cubic feet per second. The total volume of water flowing over Niagara Falls, I think, is in the neighborhood of about 150,000 cubic feet per second. So picture the Mississippi River in its greatest known peak discharge, and there's been 2 times when it's exceeded 1 million cubic feet per second. The last time was in 1993, when the great floods, if you guys remember from 1993, when these great floods came down the Mississippi River after that extremely wet summer and caused tremendous economic damage. Okay, think of that now, 1 million cubic feet per second. This flow, like I said, was in excess of 300 times as much, over 300. Nowhere on Earth today is there any flow of water remotely close to that. Another thing about this water flow is it was moving in excess of 60 miles an hour.
How deep was it?
It was estimated to be 400 feet deep. 400 feet deep.
200 pounds
missing
per
something.
square.
Okay.
How does this fit in with the fire?
Because what we're getting to here is we're seeing the evidence that we're seeing the evidence that there was something that caused an extraordinarily rapid melting. And this flow essentially was evidence of the meltdown and the scale of the meltdown. That's how this ties in, is because this is bringing us, this is the mute evidence, the stark evidence for the scale of some of this melting that was going on. It wasn't just like when we think of a glacier receding, like, you know, we're talking now in the global warming scenarios about some of the glaciers that are receding, right? And they're receding. They've been receding for 100 to 150 years since the termination of the Little Ice Age. But nowhere are there catastrophic flows even remotely close to this scale. The biggest modern flows we've seen are from breakout floods in Iceland called Jokulhaups. Jokulhaups are where, in Iceland, you've got volcanoes under the ice. They provide the source of heat that melts this ice and creates a subglacial reservoir of water, which usually within a few days to a week, under pressure, forces its way out through the glacier, which is riven with cracks and fractures and so forth, bursts out of the glacier margin and creates a catastrophic flood that flows to the ocean. They're well done. If you Google in Jokulhaups, I could spell it for you, you'll get some interesting stuff describing these catastrophic floods up in Iceland. They've also happened anywhere where there's glaciers that can temporarily block a flow of water. Now, the Jokulhaups that we've seen today are usually invoked as a kind of an explanation for what we saw happening here. But there's a problem with that. None of the Jokulhaups that we have seen today, again, remotely approach this scale. The largest Jokulhaup known in history was less than 1,000th in terms of peak discharge of this flow right here. Less than 1,000th. See, the geologists have an explanation for this. I've been examining this explanation for about 15 or 20 years now. the more I learn, the more I consider the alternatives, the more time I've spent out here analyzing the evidence in the field itself, the less sense that the conventional explanation, in fact, the conventional explanation makes no sense whatsoever. In fact, my first trip out, Bill here was with me, and he certainly can testify to some of the stuff we saw. And Bill, probably as much as anybody, knows the alternative explanations that we've been exploring, and also understands the orthodox theory and why the orthodox theory makes no sense. It just doesn't make sense.
In the hallway when we were talking to Dr.
Breckenridge.
And we talked to Breckenridge for like 30 minutes or something.
45 minutes.
45.
Yeah, we went and we interviewed a professor of geology out at Idaho State University who was considered to be one of the foremost exponents or geologists who had studied into the causes and origins of these floods. And after speaking with him for 45 minutes, it was apparent that he was under questioning. When I raised some of the issues, he made it clear. I mean, didn't you get the impression he really was not willing to commit to the conventional theory? When actually backed into a corner, he was willing to basically say, well, the current ice dam theory that most geologists have invoked to explain this just doesn't hold water. From the air, you see this pedestal rock here. From the ground, it looks like this. It's quite a magnificent piece of geology. It's 800 feet high. Now here's what you got to picture, folks. This thing is a remnant. The water came through here and it removed, you can see the far wall of the coulee. Every bit of basalt from the wall that's behind me where I'm taking the picture, through the Steamboat rock to the far coulee wall, all of that was rock that was excavated and removed and transported between 50 and 100 miles south of this position right here. And we're talking about an unbelievable amount of rock. And that's the map showing the Steamboat rock. These are an example of what would be an alluvial flow. If you look at this, you can actually see it's like frozen current flows. Look at that. You see that? Now, you got to picture what's going on here. You've got this flood flow surging through here, and it's not like clean water. It's not like if you go down to the river and it's just clean water or even muddy water. This is more like these floods, once they have entrained this bedrock and begin to excavate it, you've got a picture that this flood is almost more like a slurry. And it's flowing along with this unbelievable power of erosion. When the floodwaters, when the source of the floodwaters, when the taps were finally turned off, at the point when the ice mass had diminished, at that point the flood flows begin to stop. And as they begin to stop, they begin to build these layers like you see right here. And you would have a surge, followed by a secondary surge, followed by another surge, and each surge would build a distinct layer. And you can actually look and you can see here's a distinct layer, here's a distinct layer, and you can see that this is much greater. You see the texture of this. It's much coarser than this. But then you have another layer of highly textured stuff. So what we're seeing here is essentially the water flows that represent the residual melting of the great ice complex. That's what we're actually seeing. This is one of those dry cataracts I was telling you about. I know some of you have seen these photographs, but this thing here is over 400, no, it's about 400 feet tall. And compared to Niagara, Niagara is diminutive compared to this thing. It's estimated here that the water flow was at least as high as the cataract walls themselves. Since the cataract walls themselves are 400 feet high, the water flow over here was 400 feet. This, of course, is the classic modern example of a cataract, a receded cataract waterfall. We all know what this is, right? What is this? Niagara, of course. Well, here's the Canadian Falls and here's the American Falls. And you see the classic horseshoe shaped. And that's just simply because water flow is faster in the middle of a stream or a river and therefore is more erosive in the middle. And its erosive power diminishes as you get towards the edges of the water flow. So therefore what it does is it erodes the center of the flow quicker than the edges, and hence creates the horseshoe shape. But you can picture, now this is a good illustrative example to understand Grand Coulee. If we were able to accelerate this, either by doing time-lapse photography into the future or increasing the flow of water to accelerate the rate of cataract recession, what would eventually happen is these two waterfalls would eat their way back upstream until they met up here. Can you picture that? They would therefore leave this island rock. This is called Goat Island. They would leave that island there. Well, see, that island really is almost an exact analog for Steamboat Rock. Now, see, you can understand what it did. It went from cataract like this, and you got a picture that this cataract is essentially a fossil feature that is left over. This is where the water had eroded to at the time the taps were turned off.
Well, that cataract started, what, about 30 miles downstream and eroded to that position?
That's right. Bill is exactly right. This cataract was literally over 30 miles further south. And through the course of the flood, the cataract was eaten up current. When the current was finally terminated, this is how far it had gotten, and essentially this is where it's been, you know, for 12 or 13,000 years now. And so Steamboat Rock, if you can picture, Steamboat Rock now is just the equivalent of Goat Island. At one point, there would have been a cataract eating its way back this way and one back this way, and eventually they met. And they met in time so that the rock itself wasn't eroded away. Had the flood continued to flow for who knows how long, probably not much longer, another week or two, that rock would be gone. Now here's another shot of it where you can really see look at this, Dolores, this bedrock here. You see, this is scoured. This has sustained intense, violent, erosive flows that have come across here. Again, one can only speculate, but there was probably as much as 50 to 100 feet of basalt bedrock lowering before you even get to this level.
So it looks like it's got snaps taken when they had some snow. It really brings the detail.
Yeah.
It does.
Mm-hmm.
Brings it out.
It does. This was a picture by a great book by a geologist, photographer, and pilot named John Shelton, who did a lot of his own, did a wonderful book called Geology Illustrated that's just filled with his beautiful black and white photographs from the 40s and 50s.
Randall,
Yes.
that's all rock, or is that laid in gravel like the picture of the wall? One of the slides shows.
This is all rock. This is all bare.
Not sand and gravel.
No, it's basalt bedrock, but in the hollows you'll find there's gravelly material that's been laid, and there's actually growth on it. You know, there's.
The slide you showed us with the guy standing on the boulder, and there's layers of gravel and sand. That's
No.
somewhere downriver from here, down.
That's actually upriver,
It
upflow.
looks like there's two really big potholes forming in there too on the right side.
Yeah, see what Bill is pointing out? Potholes.
100 feet across.
You see right here, here's a pothole and here's a pothole.
They're usually 5 or 6 feet. Those things are like a couple 100 feet wide.
Well, yeah, there'd be at least 100.
Yeah.
I mean, because you figure this is 400 feet right here.
Yeah.
So yeah, that's probably 150 feet wide. Now, a pothole is another interesting piece of evidence for a catastrophic flood. Because what will happen here with a pothole is if you have multiple flows of water, particularly, and if anybody is interested in this, at some point we could do a field trip. And there's potholes all over North Georgia, Tennessee, and North Carolina. Not on this scale, but you can see some enormous potholes. Now, potholes form essentially under conditions of extreme fluid turbulence. They're not dissimilar from the way a tornado forms in the atmosphere. When you have two airstreams coming together, particularly of different temperatures, it sets up a shear that does this, and that's what creates this initial rotary motion. In terms of water flow, if you have two flows of water, like with different density, for example, if one flow of water is carrying more sediment, or one flow of water is moving faster than the other, it'll create that shear. And that shear will start this rotary motion in place, and it'll literally create the equivalent of an underwater tornado. Again, there's an Icelandic term, kolk, that's used to describe this underwater tornado. These underwater tornadoes, called kolks, they can be extremely erosive. And when they go to work on bedrock, you can actually picture them like a giant drill, just boring a hole, a circular hole, into the bedrock. And that's what we have. That's what Bill was commenting. He noticed those two potholes right there, and those were formed, again, by this rapid rotary motion, and particularly if the water flow is laden with sediment. You can just picture it. You've got this rapidly rotating funnel of water loaded with abrasive sediment, just carving its way right down into the bedrock.
So what about the fire?
Okay, so my point here, since Paul is really putting the pressure on, I better get back to the fire. Because since some of these folks, Paul, haven't seen this information about the flood, that's what I'm ultimately tying it back, because I'm trying to show that there is this source of heat. This is the entire map complex itself of Dry Falls Cataract. You can see the whole thing from left to the right of the screen is over 5 miles wide. Okay, so my point in showing you this was, again, to try to convey to you some of the evidence for these massive water flows. Before I sign off completely on this, I'm going to show you two NASA photographs of the region. Okay, first I'll show you a graphic. Okay, here, this is basically the setup. This was the condition prior to the flooding. And once you begin to look at this and you realize that you've got, estimates vary, between 6 and 7.5 million cubic miles of ice. Over central Canada, the ice was 3 miles thick. Over the region of Hudson Bay, I mean, can you imagine an ice mass 3 miles thick? Now, again, you see, all of Canada is under that ice. So 13,000 years ago, the world looked like this. Between 9 and 10,000 years, that ice was gone. See, and that's essentially the paradox that I'm proposing here, and the paradox that was recognized by scientists way back in the 70s, is that getting rid of this mass of ice requires an extraordinary amount of heat energy. Okay, so where does such a source of heat energy come from? Well, one reason why the scientists of the 70s essentially gave up and assumed the problem was intractable was any source of energy that they were trying to invoke to explain the rapid melting, all of those explanations were all Earth-based. They were all terrestrial. Whereas I believe that the solution is not terrestrial in nature.
Did the poles shift?
What?
Did the poles shift?
Well, that's a complicated question. And I don't think Paul wants me to get into that right now. So let me say this, though. I think that there was a pole shift. However, the pole shift wasn't the cause. The pole shift was the result. Because here's the thing about pole shift, people, since you brought it up. When you have this much ice mass, that affects the stability of Earth's rotation on its axis. If you can suddenly remove this tremendous mass of ice from the polar regions, it creates effects. First of all, rheological effects, which means a redistribution of mass under the crust. It causes, that's all you need to think about for now, that there's a huge redistribution of surface mass. That redistribution of surface mass is going to affect the Earth's spin. Okay?
Now then, was this ice not more or less consistent through Europe and Russia? And
No.
it wasn't.
No. In fact, during the, and here's another one of the anomalies. During the Ice Age, Siberia appears to have been warmer than it is now. that's an enigma of the whole. And you know, Siberia, remember, is up here. This
So
is
do you think then that the pole was sort of in the middle of this?
well. It's interesting that if you take the center of the North American ice sheet was Hudson Bay. That's right there where the ice was thickest. If you draw a circle around that, that's the equivalent of 23.5 degrees. It's just like, it's essentially the same size as the Arctic Circle.
Basically, you're saying that was the,
I'm suggesting that that might have been the case.
The ice sheet extended 23 degrees.
Yeah. And then those red arrows represent principal flow lines of meltwater. So the Pacific Northwest, where I was showing you Grand Coulee and some of those other features, that's all right in here. And what makes those features so spectacular is the fact that from the ice to the ocean was a short, steep distance to travel. When the ice flowed off the Midwest here, the water flowed off the Midwest, it had a much longer distance to travel at a much shallower gradient. Therefore, it didn't have the same erosive potential as this water flowing off up here, for example. So even though you can travel from the Atlantic to the Pacific, and if you know what to look for, you can trace the evidence of the catastrophic meltwater flows all the way from the Atlantic to the Pacific. And Brad and I have almost accomplished that. We're still got a couple of more trips to do. But you can very clearly see that that the evidence is all along the entire southern margin of the ice for these tremendous meltwater flows coming off. Finger Lakes of New York. How many of you have seen the Finger Lakes? Finger Lakes were created by catastrophic meltwater flows coming off right here. In fact, if you look at the Finger Lakes, they're basically just coulees that are filled with water. They're very similar to the coulees you see out west in size, in shape, in depth, just you've got a different environment. You know, if you've got 45 inches of rainfall up here and 10 inches of rainfall out west, that's mainly the difference. So where you have 45 inches of rainfall, you get a lake. Where you have 10 inches of rainfall, you get a coulee that's basically dry. So I'm going to skip through some of this real fast because we saw it last 2 weeks ago. If you go into the literature, you know, the various traditions from all over the world, you will find references to this idea of Ekpyrosis, the idea that there is this fire coming from heaven that, you know, you can find it. It's deeply embedded into the traditions of the Mayans, the Aztecs. It's deeply embedded in the biblical traditions, both Old and New Testament. You find it in American Indian traditions. You find it very much embedded in Egyptian stuff, but it's a little more allegorical there. It's harder to discover. You find it in the Norse traditions. You begin to find it. You find it in the Pacific Islanders have lots of traditions about these cosmic fires that basically wipe everything out. South American Indians, all the way down to Tierra del Fuego, the Uricaris, I think they're called, have a tradition about a great firestorm that engulfed the earth. And interestingly, in their tradition, the firestorm was then followed by a great flood. And the great flood was essentially the handiwork of the Creator who had to bring on the great flood to put out the cosmic fires. So, again, there's just both prophecies about the future and tales about the past. And we saw some of this a couple of weeks ago. We've all heard of Sodom and Gomorrah, right? The Lord rained upon Sodom and Gomorrah brimstone and fire from the Lord out of heaven. And Abraham gat up early in the morning, and he looked toward Sodom and Gomorrah and toward all the land of the plain, and beheld, and lo, the smoke of the country went up as the smoke of a furnace. So, what is it that is this something just completely conjured up, you know, in the minds of?
Shower that hit the earth.
Well, I would suspect that would be the first place to look, because I mean, after all, if we take it at face value, it's saying brimstone and fire. From where? From the Lord out of heaven. I mean, I think it's telling us pretty literally here. the Mahabharata. This is from the Vedic tradition of India. And they're talking about the end of the Yuga, the end of our current world age. And after going through this long litany of disasters, they say these all will take place at the end of the Yuga. And when men become fierce and destitute of virtue, then does the Yuga come to the end. And the course of the winds will be confused and agitated, and innumerable meteors. Notice this, innumerable meteors. So they're getting pretty explicit here. They're getting pretty darn close to what I think constitutes the solution of this problem. Innumerable meteors will flash through the sky, foreboding evil. And then the sun will appear with 6 others of the same kind, and all around will be din and uproar, and everywhere there will be conflagrations, and fires will blaze up on all sides when the end of the Yuga comes. What do you think this image of the sun with 6 others? How might we explain that by naturalistic phenomena? See, up until this day and age, the tendency has been for all of those of a scientific bent to basically consider all of this as, either allegorical or, superstitious belief in supernatural events. But it's only within the last decade or two, I think, that science has begun to sort of begrudgingly say, well, maybe some of this stuff from these ancient traditions isn't just something conjured up into illiterate fantasies of a bunch of savages who have to have some way of explaining what they don't understand. Maybe, in fact, what we're seeing here is traditions, maybe garbled or modified through successive tellings, but traditions that go back and have roots in real events. And maybe these traditions can actually give us insight into these real events. And I think that when we start adopting that position and realize that ancient peoples were a lot more educated and sophisticated than previously believed, and that many of these myths, although they sound quaint and they're loaded with imagery, bizarre imagery and so forth, once we begin to have the linguistic key for deciphering them, once we have the Rosetta Stone, so to speak, we can begin to read these myths as recollections of actual events.